So, welcome. In the last two classes, we have seen the origin of stresses and the origin of viscosity. It is in molecular motion, and the motion of molecules transfer momentum, cause force to act on different layers of the fluid. And in the last class, we have seen equations that we are going to use now in this class based on force balance, based on material balance, and so on. Right. So in this class, we are going to see several examples where we are going to talk about a laminar flow, and we are going to calculate velocities, forces, stresses, friction factor, all the things that we have done when we did macroscopic balances and when we did Bernoulli equation. All the things that we did at that point of time, we are going to calculate using microscopic balances, means using Navier-Stokes equation. And we are going to look at several examples. I'm going to give you the starting point of those calculations. I'm going to give you the importance of those calculations, applications where these kinds of situations are important in day-to-day life. Some of the maths part I'm going to do, and the remaining maths part you have to do yourself, right? So let's get started. This is where we are on topic number 6. Just to help you to revise what we mean by equation of continuity. What does it tell us? Where does it come from? Try to refresh or try to look at the derivation yourself. What is equation of motion? Derive that yourself. What does it mean? What is the meaning of all the terms? For a Newtonian liquid, what is this equation of motion popularly known as? Newtonian liquid. Okay. Liquid means constant density, incompressible. Newtonian means stress strain, linear relationship between stress and strain. Revise, answer it for yourself. That will help you to revise. So here is what we have seen. Appendix B4 gives you equation of continuity. You are going to need all these again. That's why I'm giving you these again in this lecture. Navier-Stokes equation, appendix B6. B5 gives you in terms of stress terms. B6 gives you in terms of the velocity components. Right now for this class, we are going to need this equation in the viscosity and velocity terms, because we are going to deal with Newtonian fluids. Okay, let's think about Newtonian flow through a pipe at steady state. Okay, what I want you to do is find velocity profile. What is the volumetric flow rate? Find friction factor. Remember when we were doing Bernoulli equation, when we had laminar flow, what did we do? We said friction factor is 16 by Re. Where did we get that from? We got that from the friction factor versus Reynolds number chart, Moody chart if you like, right? I had just told you F is 16 by Re. You had to just believe me at that point of time. Now I'm asking you to calculate it for yourself. Whether we can get this for ourselves using microscopic balances. That's what I want you to do here. Okay. Let me do this problem in a little bit more detail so that you know how it is to be done. First of all, if I try to give you a stepwise procedure, here is the first step. First step is decide what kind of coordinate system you would like. Okay, so it's a cylindrical pipe. Liquid is flowing along the axis. Pressure difference is there, P1 and P2. So what coordinate system would you like? Obvious, cylindrical coordinate system. Okay, so now take the Navier-Stokes equation in cylindrical coordinate system. That means these are the equations. Okay, Navier-Stokes equation in the cylindrical coordinate system. Okay. What is the flow direction? That's step number 3. What is the flow direction? Flow is in, if it's a cylindrical coordinate system, this is our Z direction. So flow is in the Z direction. So we have to take the equation in the z direction, this one, we don't have to look at this equation and this equation, we have to take this equation, the z direction. Okay. Next step, this is our equation. Next step, simplify the equation by considering some terms that become zero. Okay, let's try to do that for this particular case. Flow is steady state, so can we neglect this? This is zero. Pipe is horizontal. What can we say about GZ? Component of gravity in the z direction is zero. Flow is in the z direction. Flow is in the z direction. Is there any flow in the r direction? Is there any flow in the theta direction around the axis? Is there flow in the r direction away from the axis? No. Vr is 0. V theta is 0. If Vr is 0, V theta is 0, that means del Vr by del r is 0, del V theta by del theta is 0. Therefore, by continuity, del Vz by del z is 0. Flow is not accelerating along the z direction. Flow is not decelerating along the z direction. Flow is moving at a uniform velocity. There is no dvz by dz. There is no elongation. There is no compression. So dvz by dz is 0. Mind you, Vz is not 0. But dvz by dz is 0. If dvz by dz is 0, what about del square vz by del z square? That is also 0. Does Vz vary in r direction? Yes, Vz varies in r direction. Right? It can be a very high value near the pipe, center of the pipe, very low near the wall. So this is important. This is non-zero. Does Vz vary in theta direction? No, it is symmetric around the theta direction. This is 0. Does pressure vary in the z direction? Yes, pressure varies in the z direction. Pressure changes from P1 to P2 from z is equal to 0 to z is equal to L. If you want, take this is z is equal to 0, this is z is equal to L, other end of the pipe. Okay. So our equation now becomes 0 on the left hand side, or we could have simply said that flow is laminar, which means Reynolds number is small. Recall the scaling things that we did. Reynolds number is small means all convective terms become 0. So 0 on the left hand side, steady state. So minus dp by dz plus mu 1 by r del by del r of r dvz by dr. Okay. I hope everybody gets up to this point. If you don't, think and get it up to yourself, up to here all by yourself. Then only go forward. Okay, so our simplified equation is dp by dz minus plus mu 1 by r del by del r of r dvz by dr. One word of caution, this delta p by delta z, right now I have made it as dp by dz. Why? Because pressure is not varying in r direction. Pressure is only varying in z direction. Vz is not varying in any other direction. Vz is only varying in the r direction. So I have made this as a total derivative, not partial derivative. Okay, and therefore this also should be total derivative. It should be d by dr. It should be d by dr. It should be d by dr. D by dr, not partial. Okay, dp by dz. What is that? It is P2 minus P1 divided by L. I can say it is same as minus of P1 minus P2 by L. P1 minus P2 we have been saying delta P minus delta P by L. So dp by dz is minus delta P by L. Where do we get delta P from? Measure from either manometer or some pressure sensors and so on and so forth. So our equation becomes mu 1 by r d by dr. Now this is also total. D by dr is also total r dvz by dr. Understand the difference between partial derivatives and total derivatives. Vz only varies with r, no other. Pressure only varies with z, no other. So this is a second order differential equation. Second order differential equation in R. To solve, I need boundary conditions. How many boundary conditions do we need? Two boundary conditions. Let's look at the boundary condition. That's our next step. Determine the boundary conditions. So can you think of boundary conditions with respect to R? Here they are. At R is equal to capital R, Vz is 0. Meaning at R equal to capital R is describing the wall of this pipe. At the wall of the pipe, we are going to say no slip condition, means the fluid has the same velocity as the pipe. Pipe is stationary, so fluid is stationary just at the wall of the pipe. So we can say that at R is equal to R, Vz is 0. This is called as no slip boundary condition. There is no slip, no relative velocity between the pipe wall and the fluid in the immediate vicinity of the pipe. At R is equal to 0. At R is equal to 0, what can we say? Symmetry. If it is symmetric, we can say gradient of Vz with respect to R is 0, or more specifically, we can say R dVz by dr is equal to 0. If you use these two boundary conditions, can you evaluate this equation now? Do that for yourself. Pause the video. Here's the answer. So now step 7 is we solve the differential equation along with the boundary condition. That's step 7. So I've given you 7 steps. Follow them. You will be able to solve any problem. So integrate it once. So bring mu on the other side. Integrate it once. You will get d by dr. Oh, this is all total derivative. Let's make that change. Let me make that change everywhere. Oh, this is also d. 1d has remained. I have changed all the things. This 1d has remained. It is d. So integrate once. You will get this equation. Now if I use second boundary condition at r is equal to 0, at r is equal to 0, dvz by dr is 0, r dvz by dr is 0. That means C1 must be 0. Integrate again. You will get Vz as minus delta P by 4 mu L r square plus C2. If I use the first boundary condition at r is equal to at r is small r equal to capital R, Vz is 0. So C2 I will get delta P capital R square divided by 4 mu L. Now I can simplify. I'll get Vz as delta P R square by 4 mu L into 1 minus R by R square. We had seen this earlier. This is a parabolic velocity profile. Okay. What is the maximum velocity? Maximum velocity is at the center. R is equal to 0. That's delta P R square by 4 mu L. So I can say Vz is equal to V max into 1 minus R by R the whole square. How do I get flow rate? Flow rate, if I take a differential element, flow rate, it is Vz multiplied by area perpendicular to Vz. Recall from previous lectures, area perpendicular to Vz. Area perpendicular to Vz is R delta theta delta R. That is in one such differential element. I have to add up all such differential elements, means if this is the pipe, I have to take differential elements, let's say one differential element, second differential element, third, fourth, fifth, sixth, seventh, eighth, all such differential elements, which means the R direction I have to integrate from 0 center to capital R, and theta direction I have to integrate from 0 to 2 pi. Okay, visualize. So if you substitute this V max into 1 minus R by R square, we had done this earlier. So I am just directly giving you the result. V average will be Q divided by pi R square, which will be V max by 2. V max by 2. Which means delta P R square divided by 8 mu L. This equation, if I write it differently, if I write it in terms of delta P would be 8 mu L V average L by R square, and R square I can say is diameter square divided by 4. Take that 4 on the others, on the numerator it becomes 32 mu V average L by D square. You would have seen this equation earlier called as Hagen-Poiseuille equation. You may not have known where this comes from. Wonder where it has come from now. It has come from microscopic momentum balance. It has come from Navier-Stokes equation. Navier-Stokes equation is allowing us to directly get Hagen-Poiseuille equation for ourselves without any experimental data, without anything. Just solve the Navier-Stokes equation. That's the beauty and importance and applicability of Navier-Stokes equations. Let's go forward. Stress at the wall is tau w. Tau is minus mu dvz by dr. What is dvz by dr? Here, dvz by dr is minus delta p by mu l into r by 2. Oops, this should also be total d, not delta, d okay. Yeah, mu dvz by dr. So mu minus delta p r mu l by 2. Cancel this minus, cancel this mu, it is delta p r by 2l. What is the force at the wall? Force at the wall will be when this r is equal to capital R, which means I am substituting for this at r equal to capital R, which means it is delta p r by 2l. If I substitute this r in terms of d, it is delta p d by 4l. Recall tau w, when we had looked at friction factor in pipes, what equation did we start with? We started with overall force balance, delta p multiplied by pi by 4 d square. Recall those lectures when we talked about friction factor in pipe is equal to delta, sorry, let me erase this. I was saying something and I was writing something. Delta p multiplied by pi by 4 d square, that is the force, pressure force, that must be equal to the force at the wall, tau w multiplied by pi dl. We have got this expression from overall force balance. Same expression we have got now based on Navier-Stokes equation, based on microscopic balances integrated to the whole pipe. That's the advantage and that's the beauty of Navier-Stokes equation. If you like, if you see how tau varies with respect to r, tau is 0 at r equal to 0, right? Tau is 0 at r equal to 0. Tau is 0 at r equal to 0. Tau is maximum at r equal to capital R. So if you plot the tau on this axis, so what we are plotting is tau on this axis and r on this axis. Tau w is at the wall, that is the highest. It varies linearly, it goes to 0 at the center. Tau varies linearly with the location in the pipe. That's the meaning of this equation. Now if tau w is delta pd by 4l, can I divide tau w by half rho v average square to get us the friction factor? I'll do that. Put this delta pd by 4l for tau w. I will get this expression. If you substitute now delta p from Hagen-Poiseuille equation, this, you will get friction factor is 16 by Re. Now you see the beauty of Navier-Stokes equation. Using Navier-Stokes equation, we have been able to get friction factor as 16 by Re without doing anything. We only had microscopic force balance. Only based on that microscopic force balance, we got friction factor as 16 by Re. That's the importance, that's the beauty, that's the applicability of Navier-Stokes equation. If I give you Navier-Stokes equation, if you can integrate, you can get all the things that you want: forces, friction factor, flow rates, relationship between the average flow rate and the maximum flow rate, you name it, and we can get it. Overall macroscopic force balance, all that has come from Navier-Stokes equation. Okay, let's take some more examples. Flow between two parallel plates. So imagine that there is a plate here. Imagine that there is a plate here and another plate here. Now we are going to look at two cases. One case where the top plate is moving to the right with a velocity v and bottom plate is stationary. Second case we are going to do is two plates and I apply pressure difference between the two, P1 minus P2. P1 is higher, P2 is lower, liquid goes from left to right. This is called as a Couette flow. Couette flow, and this is called as a Poisson flow. Poisson flow. Okay. Importance of this. So if you are looking at, let's say, coating, so imagine this liquid that is, or the fluid that is here between the two plates is a polymeric liquid, and I want to coat that polymeric liquid on a surface, let's say this plate. All the coatings that you do are made in this way. The molten polymer is here, the liquid is, the plate is moved, polymer gets pulled, so polymer gets coated along with the fluid, along with the plate, and once it is coming out of the gap between the two plates, it is immediately quenched, so the polymer solidifies. So I have a layer of polymer solidified on a plate. That's how I coat materials. All the polymer coated bags that you get, they are coated in this way. Another example is bearings. In bearing you have a fixed part and you have a rotating part. In between you have a fluid. So that fluid is supporting the rotation of that bearing. It's like a very small gap between the two surfaces. One is rotating, but if you are looking at a narrow view, curvature is neglected. It's like flow between two parallel plates. Example of Poisson flow. If I want to make a polymer slab, I will have a molten polymer between the two plates, apply a pressure gradient, polymer will flow, and when it comes out, I will quench that polymer solidifies, we will get a slab of the polymer. That's how bags are made, polymer bags are made. And then you chop them and you blow them, you get a bag of polymer. Okay? So these examples are very important. Steps. What are the steps? These are the 7 steps we have seen. What I want you to do, find the velocity profile, flow rate, stresses at the wall, friction factor, and so on and so forth. Do this for yourself. Pause the video. Here is the solution. Couette flow, if you see, what is the equation in which direction flow is occurring? X direction. Let's look at all the steps. Coordinate system, Cartesian, okay, flat plates. Navier-Stokes in the Cartesian coordinate. Flow direction, let's say X direction. Take the equation in the X direction, simplify. This is the equation in the X direction. Let's simplify. Let's simplify for this case. Okay, this case you do for yourself. This is homework. We are going to simplify for the Couette flow case. Steady state, this is 0. Flow is in the X direction, there is no flow in the Y direction, this is 0. There is no flow in the Z direction, this is 0. Continuity equation tells us del Vx by del X equal to 0. I am talking fast, but each sentence you make sure you understand. Flow is by motion of the plate, it is not because of pressure in case of Couette flow, so this is 0. In case of Poisson flow, this term will be there. Vx is not varying with X, this is 0. Vx is not varying with Z, Vx is only varying with Y, this term remains. Plates are horizontal, this is 0. So I get d square Vx by dy square is equal to 0. What are the boundary conditions? No slip condition at both the walls, both the plates. At y is equal to minus h, Vx is 0. At y is equal to plus h, Vx is V. Do this for yourself for Poisson flow. For Poisson flow, if you want me to quickly write, let me write this quickly. For Poisson flow, only this term will remain. This term will also remain for Poisson flow. Then you will get minus mu d square Vx by dy square is equal to minus delta P by L, like we had earlier. Boundary conditions would be at y is equal to 0, symmetry, dvx by dy is 0. Look at this, dvx by dy is 0. plus H minus H, Vx is 0. No slip condition. So you can use any two out of the three because it's a second order differential equation. You can use this and this, you can use this and this, you can use this and this. Any two out of the three can be used. It's a second order equation. Okay, let's do it for cuvette flow. This is what we are doing, cuvette flow. Poisson flow is homework. Vx is equal to V by 2 1 plus Y by H. Flow rate is Vx multiplied by area perpendicular to Vx. Area perpendicular to Vx is delta Y delta Z. Notice. Integrated from minus H to plus H. Delta Z, let's just say, is W integrated with respect to Z. It's just W, some width of the plates. That's the width of the polymer coating that we want. That's the width of the plate that is to be coated. Tau W at the top plate is mu dVx by dy at H. Tau W at the bottom plate is mu dVx by dy at H. It's minus H. Okay. Make sure, take care of the signs. Okay. Whether it is minus sign, plus sign. Vx is varying, increasing with Y. So there is no need for a minus sign. Okay. So check the microscopic force balance in the sense now there is no pressure force. Whatever is the force that is applied on the top plate. So if you go from here, this multiplied by area of the top plate, you will get force on the top plate. This, if you multiply by area, you will get force on the bottom plate. Macroscopic force balance means both these forces have to be same. Whatever force we have applied to the top plate, same force will be transmitted to the bottom plate. It's a Cartesian coordinate system. So these two forces have to be equal. Make sure that you get them equal. They will be equal. I can get friction factor. Tau W divided by half rho V square. V average. Q divided by area. W to H. Okay. Do this for yourself. Let's go to the next problem. Next problem is similar. Cuvette flow and Poisson flow. Now it is between two cylinders. So imagine that there is an inner cylinder of radius R1 and an outer cylinder of radius R2. Gap between them is filled with some liquid, viscous liquid. Inner cylinder is solid, like a solid rod. Outer cylinder is hollow. So this solid rod is inside that hollow cylinder. Poisson flow means I am applying pressure difference P1 minus P2, making the fluid between the cylinders move to the right. Cuvette flow means I am not applying pressure gradient, but I am making the inner rod move to the right with a velocity v. So this fluid will get dragged, will get forced along with this cylinder. Application. So imagine you are making a wire. Let's say this inner rod is like the wire and this liquid is like the polymer, molten polymer. So when you draw that wire out, the polymer, liquid polymer, molten polymer flows along with this rod, along with this wire. Now once it is outside, we can quench and solidify the polymer. You will have a rod coated with a solid polymer. That's how insulated wires are made. Copper wire is there, insulation, plastic insulation is there, right? Or Poisson flow here. There is a molten polymer, there is a rod here, there is a hollow cylinder here. The gap between them is filled by a polymer, molten polymer. I apply pressure difference, this polymer flows. As it comes out, I solidify the polymer. What shape it will take? It will become a pipe, solid polymer pipe. Inner radius of that pipe will be R1, outer radius of that pipe will be R2. That's how pipes are made. In fact, that's how all the extrudates are made. All the extrusion processes are like this. Okay, So one of them is homework for you, one of them I will explain. So now this is homework. Cuvette flow is homework. We will do Poisson flow. Okay. So decide the coordinate system, take Navier-Stokes equation, all those things. So here in this case we have to have cylindrical coordinate system. Along the z-axis is the flow. So we'll take equation of motion in the z direction. This is that equation of motion in the z direction. Cuvette flow is homework. Poisson flow I am explaining. Let's simplify. Steady state. Flow is only in the z direction. There is no Vr, there is no V theta. From continuity, del V z by del z is 0. I am just telling you very, very quickly, but you make sure you understand why we are cancelling every term. Vz does not vary with theta. Flow is symmetric. Vz does not vary with z. No compression, no elongation, because del Vz by del z is 0 from continuity. No component of gravity in the z direction. Cylinders are horizontal. Pressure gradient we have applied, that remains. dvz by dr, that remains. So we will have mu 1 by r d by dr of r dvz by dr is equal to dp by dz, which is same as minus delta p by l. That's the pressure gradient that we have applied. Boundary conditions. No slip boundary conditions at both the solid cylinder surfaces. Flow is occurring by pressure. Cylinders are not moving. No slip condition. So boundary conditions at r equal to r1, Vz is 0. At r is equal to r2, Vz is 0. No slip. So if you integrate, you will get Vz is minus delta p by 4 mu l r square plus C1 ln r plus C2. Incidentally, in the Bird-Stewart-Lightfoot's book, Transport Phenomena, both these problems are solved problems. The cuvette flow is a solved problem. This is not a cuvette flow. Is not a solved problem. It's a problem for you to do. It is 2b.7. Okay, but the answers are given there. In the Bird-Stewart-Lightfoot's books, section 2.4, Poisson flow between two cylinders is a solved problem. So beyond this, solution is given. So you can check for yourself. You can get the flow rate, you can get the stresses, all those things you can get. Velocity profile, flow rate, stresses, friction factor, all those things you can get. Next problem. Okay. Flow of a falling liquid film due to gravity. So imagine that there is a wall. Imagine that there is a wall and the liquid is falling next to the wall. It is sliding on the wall, if you like. Liquid is sliding on the wall. Example, imagine that suppose there is a windscreen, car windscreen, rain is falling, rain is sliding, water is sliding on the glass windscreen. Or imagine that this wall is cold, I have vapor that. So vapor condenses, vapor comes in contact with this cold wall, vapor condenses, becomes liquid, and this liquid falls down, drains. So it is important for condensation heat transfer. Semester, when you do heat transfer, this will become very, very important. Condensation heat transfer. Another example, let's say we want to coat this wall. Another way of coating this wall, plate, if you like. So that plate is put in a molten polymer mass and the plate is pulled upwards. Plate is pulled upwards. So relative to the plate, the molten polymer is draining down. And then the polymer solidifies and we get a coating of a polymer on this wall. That's the example. That's the importance. Okay. It's a solved problem in section 2.2 in the Bird-Stewart-Lightfoot's book, Transport Phenomena. What I wanted to do is relate the film thickness delta to the flow rate of the liquid. That's what I wanted to do. Okay, 7 steps we know. In this case, let's take Cartesian coordinate system. Let's say this is the y direction. This is the z direction. Let's take Navier-Stokes equation in the y direction. This is the Navier-Stokes equation in y direction. Let's simplify. Steady state. Vx is 0, Vz is 0. By continuity, del Vy by del y is 0. Flow is fully developed. Flow is by gravity. There is no pressure. Pressure everywhere is atmospheric. There is no pressure in the gradient in the y direction. Vy does not vary with x. Vy does not vary with y. Vy varies with z. And Gy is 9.81. Gy is there. So if you simplify, you will get mu del square Vy by dz square is equal to minus rho g. Boundary condition, if this is our origin at z is equal to 0, it is the interface between the liquid and the air. What we are saying is air has very low viscosity. There is very little momentum being transferred to the air. If there is very little momentum being transferred to the air, tau at the liquid surface is 0. If tau at the liquid surface is 0, mu of the liquid is not 0. That only case that can be is when dvy by dz is 0. This is called as a free slip condition. Means the velocity of the liquid can be anything. It is totally independent of the air velocity. There is complete slip between the air and the liquid. Liquid movement is not hampered, or liquid movement is not because of the air. If it was a solid wall and that solid wall was stationary, we would have said Vz is equal to dvy, Vy would be 0. No slip. But air, because of very low viscosity, we are going to say no stress, no force transmitted. No force transmitted means no tau. No tau means no dvy by dz. So at z is equal to 0, dvy by dz is 0. At z is equal to delta, no slip condition at the wall, Vy is 0. Okay, integrate. You will get Vy is rho g delta square by 2 mu 1 minus z by delta the whole square. If you plot that, this is how it will look like. If you are plotting velocities here at this location in the y direction, velocity is 0 here. Velocity is slightly more 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 here. And no velocity gradient, means dvz by dvy by dz is 0. So this velocity profile is parabolic. Parabolic. Quadratic if you like. Parabolic. Okay. Flow rate. What will be the flow rate? Vy multiplied by area perpendicular to the y axis. Vy, area perpendicular to the y. So dx dz. And if you want to integrate in x direction, that is nothing but the width of the plate that you have. Width of the plate of the wall. So in the x direction, it just gives you the width. It is not varying in the x direction. This is just the width. Zero to delta. Integrate for yourself. You will get Q is equal to rho g w delta cube by 3 mu. I can multiply this by rho and divide by w. I will get Q rho by w. That's called as mass flow rate per unit width. It is denoted by a symbol gamma. It is very important in heat transfer when you start doing heat transfer. Gamma would be rho square g delta cube divided by 3 mu. Or I can write it in terms of delta. Remember, this gamma is mass flow rate, kg per second. Mass flow rate per unit width per meter, SI unit. I can write it in terms of delta. Delta is 3 mu gamma by rho square g whole thing raised to 1 by 3. This result you are going to use again and again in heat transfer. It is very important result for coating applications as well, whenever you are trying to draw a plate vertically from a molten polymer solution. Average velocity would be flow rate divided by cross-sectional area, W into delta. So V average would be rho g delta square by 3 mu. If I have to define equivalent diameter, how will I define? Equivalent diameter would be 4 times flow area divided by wetted perimeter. So 4 times flow area, W into delta, divided by wetted perimeter. Wetted perimeter is W. That's 4 delta. If I have to define Reynolds number for this flow, Reynolds number is D, V average, rho by mu. Simplify, D equivalent is 4 delta. V average, we know V average. Rho, mu. Simplify, you will get it as 4. You simply use this expression. You will get Reynolds number is 4 gamma by mu. Again, in heat transfer, you are going to require this 4 gamma by mu. Reynolds number is 4 gamma by mu. It will tell you very quickly whether flow of that film is laminar or not laminar. Force balance, if I want to do, tau W would be minus mu dvy by dz at z is equal to 0. So simplify, if you take this expression, differentiate and put z is equal to 0, you just get rho g delta. So tau W is nothing but rho g delta. Total force on the plate, multiply this by WH. WH is the height of that plate, if you like. Let's look at that. Height is this H, if you want, capital H. This whole height. And W is the width perpendicular to the screen, as you see. That's the area on which that tau W is acting. So tau W multiplied by WH is the force on the plate. If you simplify, you will just simplicate it as rho g multiplied by delta multiplied by W into H. So delta multiplied by W into H is just the volume of the liquid, multiplied by rho multiplied by G is just the force on the liquid, which means force acting, gravitational force acting on the liquid is exactly balanced by weight of the film, is exactly balanced by force at the wall. That's why there's no net force acting. That's why the film is not accelerating. It is going at steady state. Steady state in the sense Vy is not changing with Y. Vy is not changing with Y. There's no acceleration. Why there is no acceleration? Gravitational force acting on the liquid is exactly balanced by the frictional force, stress at the wall. Okay. All these results are very, very important. You are going to use them in your heat transfer course. All of them are coming straight from Navier-Stokes equation, straight from microscopic force balance. Microscopic force balance. That's the advantage. The macroscopic quantities like force, stress, friction factor, Reynolds number, flow rate, average velocity. How does the average velocity change relate to the maximum velocity? All those are calculated directly from Navier-Stokes equation, from microscopic force balance. That's the beauty and advantage of Navier-Stokes equation. Whatever you need, you can get from Navier-Stokes equation. If you want, you can forget all the first parts of the lecture, first 5 parts. We had all these parts, right? We had all these 5 parts. All these things we can get from Navier-Stokes equation. We have got them for some applications. If you want, you can now forget about all this and just use the microscopic balances. Everything that you did in these 5 topics, you can get by only one microscopic balances, and you have to simplify and you have to be able to integrate either analytically or numerically. That's why the microscopic balances, Navier-Stokes equations, are so powerful and they're so important when you deal with fluid mechanics, when you deal with flow of fluids. One last example. flow between two rotating cylinders. Flow between two rotating cylinders. Okay. Imagine that there are two cylinders like this. There is an inner cylinder that's stationary, and there is an outer cylinder that is rotating. It's rotating in the anti-clockwise direction. It is rotating at a velocity omega naught. Okay. I wanted to find out what is the torque on the inner cylinder. There is a very important reason why we are finding out this torque. We'll talk about this in a while. Okay. All the 7 steps you already know. Flow is in the tangential direction. Radial tangential cylindrical coordinate system. We take Navier-Stokes equation in the theta direction. This is the equation. Simplify. Steady state. No velocity in the r direction. No velocity in the z direction. No v theta by del theta. V theta is not varying with theta. It is symmetric. This one extra term is there in the theta directional equation of motion. This is called as a Coriolis force. Coriolis force. Let me just take you back a little bit. The equation of motion in the r direction and z and theta direction. Let me just tell you that. We have that here. Yeah, we have equation of continuity. Yeah, we have equation of motion. So if you look at the r direction, this extra term is there, minus v theta square by r. That's a centrifugal force in the r direction arising out of rotation. When we did centrifuges and all that, when earth is rotating, the radial force acts on the air. It is rho v theta square by r. This is a Coriolis force, Vr v theta by r. That's an extra term. So Coriolis force comes into picture whenever there is Vr and whenever there is v theta. Like on the surface of this earth, there is v theta component and there is a radial component of the air. So Coriolis force comes into important. It is a very important force in determining the weather. There are something called as Coriolis mass flow meters that actually measure the magnitude of this force. For that, we make the fluid go in the r direction, and we also give it rotation, allow it to go around a bend, and then you measure the force on the bend. That's how the Coriolis mass flow meters work. Go back to our problem now. Where were we? Right. Coriolis force we talked about. Pressure is not driving the force. What is driving is the rotation of the outer cylinder. There is no v theta variation in the theta direction. V theta is not varying in the z direction. There is no Vr generated. There is no component of gravity in the theta direction. You can think of these two cylinders. We are looking at the plan view. We are looking at the plan view. So gravitational force is perpendicular going into or coming out of the plane of the screen. So there is no component of gravity in the theta direction. So our equation just becomes d by dr, 1 by r, d by dr of r v theta. Boundary conditions. At r equal to capital R, that is the outer cylinder, v theta is omega naught into r, and omega naught is just 2 pi n. N is number of revolutions per second. Omega is the angular frequency, omega naught. So v theta is r omega naught. At r equal to kr, k is a ratio, so k is just the ratio of the inner cylinder, the radius to the outer cylinder radius. So k is less than 1. K is less than 1. At r equal to kr, v theta is 0, inner cylinder is stationary. So if you use these two boundary conditions, integrate this, you will get this expression. Put these two boundary conditions, you will get this expression. If I want forces on the inner cylinder, I have to get torque. So before I get torque, I need to get force. Force multiplied by the radial distance will give me the torque. Force would be tau r theta. You will get from this expression. This is 0. Vr by v theta is 0. Put this divide by r, differentiate with respect to r. you will get the force multiplied by area of the inner cylinder. Area of the inner cylinder is 2 pi kr, 2 pi kr, that's a perimeter, and let's say L is the depth perpendicular to the screen. So that's the surface area of that inner cylinder. Try to visualize. These cylinders are like this, right? If you look at the elevation, this is the inner cylinder and this is the outer cylinder. This is the axis, and this outer cylinder is rotating, the inner cylinder is stationary. We are looking at the surface area of this inner cylinder. So if this is L, is the length of the cylinder, then torque would be force, this multiplied by area will give you the force multiplied by the radial distance kr will tell you the torque. So torque, you will find torque is proportional to omega naught, proportional, and it is linearly dependent on viscosity. More viscous the fluid, more is the torque to get the same RPM. We can measure the torque and use that as a means to find out the viscosity of the fluid. We'll do that in the next class. How do I measure viscosity of the fluid? So based on all this, now homework for you from Bert Stewart's Lightfoot's book, Transport Phenomena. Solve problems B2B.6. It's a problem, unsolved problem in the exercise back after the end of chapter 2. 3.63, that's a solved problem. 3A.1, unsolved problem. 3.6-4, that's a solved problem. Solve these problems yourself. They are all based on all these things that we have talked about. So understand that using Navier-Stokes equation, we can get all the macroscopic things that we want. All the macroscopic things that we want. Okay. Next class, what we are going to do, couple of things. First of all, we are going to talk about non-Newtonian fluids. And second thing, we are going to talk about how do I measure the viscosity, okay, for a Newtonian or a non-Newtonian fluid, both. Okay. So revise all the things before you go to the next class. Make sure all the things are understood well by you. Let's stop here.